So the work is on automatic differentiation for sparse tensors. So everybody here definitely knows what are sparse tensors. Let me first motivate the automatic differentiation. So usually in optimization problems, we are using a class of algorithms referred to as gradient descent-based algorithms, which are basically consisting of iterative procedures where at each iteration we have to update the parameter, here in this case it's referred to as theta, by computing the slope of an objective function. And in order to compute the slope, we have to compute the derivative of a function. And automatic differentiation or differentiable programming is basically a systematic approach to compute the derivative of a function. And in many cases, we want to represent the functions as programs. So in very high level, what automatic differentiation does is that whenever you have a function from Rn to Rm, it's going to compute another function from Rn to a matrix of size m by n. And this new function is actually referred to as the Jacobian matrix. So it returns basically the Jacobian matrix at every point that we pass to it as the input. And if I want to say what is again AD in even more high level, actually at the type level, so whenever we have an object of type some number, so what the AD is doing is that it translates it into a dual number. So what is a dual number? It's basically a pair where the first part is the original part of the computation and the second part is basically the tangent or the slope or the derivative. And we can recursively apply the same transformation to arrays. So basically arrays of numbers are going to be translated to arrays of dual numbers. Or similarly, actually, we can also consider it as, instead of array of struct, as a struct of array. And also we can translate it to the function level and also to a record of values. And the current state of affairs for the AD, we can actually classify it into two categories. So the first category involves the tensor libraries such as TensorFlow and PyTorch, where we are going to specify a function. So here we are specifying a function that computes the dot product of two vectors. And then it has an API like Jacobian or gradient, where we are specifying that what kind of differentiation we are interested in. And also there is similar work on both functional and imperative languages. So here I'm showing the work on functional languages. So for example, for F# and a subset of that, there are work like diff# and diff smooth. And the main limitation of the current state of work is that they are mainly only supporting dense tensors, and they lack the support for sparse tensors. And if you use, for example, TensorFlow or PyTorch and try to compute the Jacobian or the gradient of some computation that involves sparse tensors, you're going to get some cryptic type runtime errors, which are basically because, for example, it says that, oh, the reshape method is not implemented, or something similar to that. And for example, for other line of work, which are basically DSLs, the type system of those DSLs actually doesn't support the sparse tensors at all. Or even if it supports it, it is not expressive enough to capture all the efficient algorithms that you can express on top of sparse storage formats. So what are the challenges? So one of the key challenges, as Fred has mentioned in the first talk, is basically the functions that we want to differentiate. Usually they require some control flow constructs or somehow some user-defined functions. And it actually goes beyond the tensor algebra. So this means that we cannot perform the differentiation at the level of the tensor algebra we need something more than that. And also, if you want to do it at a kind of lower level, sparse tensor programs, if we express them as in C, for example, they are very complicated. They involve complicated data formats such as CSR, CSC, and CSF. And also, if you look at the code, they are very imperative loopy code because we need to, in some cases, implement the co-iteration. And so, what do I mean by sparse storage format? So I don't need to talk that much about it here, but basically you can see that, for example, in the CSR representation, we have basically 3 arrays, and size of the arrays are not necessarily the same here, especially if you see, for example, the DCSR format. And our solution is basically to separate the concerns. So we are introducing a 2-level DSL where at the logical level, the logical level is expressive enough to basically capture tensor algebra and more operations for control flow and user-defined functions. And nevertheless, it can also we can perform automatic differentiation on top of it. And then we have a lower level language, which is actually, we call it the physical variant of our DSL, which can capture different sparse data layout and storage formats, and also it can express the algorithms that require, for example, co-iteration, and in order to implement actually the kind of computationally complexity computationally efficient algorithms. So the high level architecture is that first we start from the logical variant of the DSL, we perform the automatic differentiation, we are going to again construct some program in the same level of abstraction, and at the end we are going to convert it down to make it storage aware. They use the compressed storage for the sparse representation. So let's start with the logical level of the language. So the logical level is built on top of our AD-agnostic work on semi-ring dictionaries. So basically, semi-ring dictionary is a dictionary where, as the value part, it can have an arbitrary element that forms a semi-ring structure. And here, for example, for representing a sparse matrix, we can have a 2-level semi-ring dictionary, where as the first level, we are mapping each of the row indices to a dictionary that represents each of the sparse columns. So, for example, here you can see that this level of dictionary represents the row indices, and here at this level, we are representing each of the sparse columns. So as a result, the element at row 1 and column 1, it can be accessed by first accessing the semi-ring dictionary associated to row index 1, and then going through that dictionary and access the element associated with column 1. And by relying on this data structure, we can basically we initially presented a language, a domain-specific language, where we can perform, among other things, also linear algebra and tensor algebra operations. So here I'm showing the vector dot product between A and B. So basically what we are doing is that we are iterating here over the semi-ring dictionary for vector A. So, and here, iteration over the semi-ring dictionary A involves accessing to the key value pairs I and A, where I specifies the index and A specifies the associated value. And then at each iteration, we are multiplying the value of A by looking up, by finding the element associated to index I from B. So this basically is the representation of vector dot product. And how can we represent now AD in this language? This is the high-level API. So this part is the same as what we have seen in the previous slide. And basically, we are saying that we are interested in computing the gradient with respect to B. And let's see what our compiler does behind the scenes. So we have a novel automatic differentiation technique, which we refer to as tensoride automatic differentiation, which basically what it does is that it's going to perform some sort of automatic differentiation rules, and this ugly and big expression basically represents the differentiation of this program with respect to B. But this is ugly and this is inefficient, so what we do is that we perform a bunch of optimizations and we derive the following program, which is basically what it's doing is that it's iterating over A and it's creating actually the bindings of A of the index to the associated value. So this is basically the same as the sparse vector A that we had initially. And as the second component, so we are performing, now that we have computed the differentiation, we have to basically also combine it with the storage representation that we are using for the sparse matrix. And this relies on our recent CTSTA'23 paper, which we have to, which we will present it in Seattle in the upcoming week, where in this physical language basically is expressive enough to capture both the tensor computation as well as the storage specification. So we are going to combine the program that is the result of these two components, and then we throw a bunch of rewrite rules and use an optimization technique known as equality saturation in order to optimize the program. So let me tell you in high level. So this is basically an example of expressing matrix multiplication in this language. And however, this language also is expressive enough to capture also the storage specification. So for example, here you can see the CSR representation. And in this language, we have captured how we can construct the logical representation, the semi-ring representation from the CSR representation. And now, whenever we compose these two, it's semantically correct. However, it's going to be very inefficient because we basically are constructing an intermediate dictionary and then we are iterating over it. We are consuming it. So this is basically the classical functional language technique referred to as the deforestation. So we have a component where we have a database of semantically equivalent rewrite rules. So for example, we have a loop fusion or deforestation rule, which specifies that whenever you're constructing an intermediate dictionary and you're iterating over it, you can basically remove the intermediate dictionary that you constructed. And one of the more important rules which relies on the semi-ring structure of semi-ring dictionaries is basically the factorization rule. Whenever in the body of a summation, we are multiplying the elements, some function over the elements of the dictionary with some constant which is invariant with respect to the dictionary, we can factorize it outside. So this corresponds to the factorization rule from mathematics. And at the end also we are, as I said, we are using the equality saturation technique, for which we are using the X system from the University of Washington, where the main data structure for that is an E-graph, which basically specifies a compressed representation of the search space. And of course, whenever we compare now over several sparse matrices for some kernels such as BATAX or computing the summation of a matrix vector multiplication, we basically see that we are going to get from 1 to 2 orders of magnitude performance improvement. And this gap is going to be enlarged as we basically see that as the matrix gets sparser and sparser. And the reason is because for PyTorch and TensorFlow, we had to convert the sparse tensors into the dense tensor. Otherwise, they couldn't perform the gradient computation. So to summarize, I've presented the AD for sparse programs which used a two-level DSL, where the logical level of the DSL was used for computing automatic differentiation, and the physical level was used to express the sparse compressed formats. And then we have used some automatic differentiation agnostic rewrite rules together with the equality saturation technique in order to optimize it. And for the future, we want to investigate how we can use these DSLs in order for sparse neural networks or graph neural networks. And for that, the main component that we require is GPU code generation. Thank you so much.